Section 3.3 takes a look at what I think is one of the neatest theorems in all of pre-calculus, and that's the rational root theorem. And basically what this is, this rational root theorem, is a way to help us factor polynomials that are 5th, 6th, 7th, 8th power quite quickly, almost in a way that guides our guess and check to find all the rational roots of a polynomial. Now, rational roots means the answer is a fraction. We can set that factor equal to 0 and we'll get a fraction for our answer. Might be a whole number too. The idea is if f of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2, and so on and so on and so on, all the way to a sub 1 x to the first plus a sub 0. Basically any type of polynomial, 5x to the 5th plus 2x to the 4th plus 7x to the 3rd plus 6x squared plus 2x plus 9. Any type of polynomials. Then all rational roots are of the form p sub I divided by q sub I, where p sub I is a factor of a sub 0, and q sub I is a factor of a sub n. In other words, all the factors of the last term should be considered for the numerator, and the factors of the first term, the coefficient at least, should be considered for the denominator. It's probably easier to see what's happening when we look at a couple examples, and so we're just going to do 3 examples today. The first example, we're going to try and factor 6x cubed plus 13x squared minus 19x minus 12. And in order to factor this, we're going to identify our p's are always going to be the last term. P is 12. And so we list the factors, I should label it clearly, the factors of p, or the factors of 12. Well, 12 is divisible by 1, 2, 3, 4, 6, and 12. It's all the factors that divide into 12. Q is the first number, which is 6. So then we will consider the factors of 6. Well, the factors of 6 are 1, 2, 3, and 6. The way we figure out our possible roots, rational roots at least, is we take all the top line and put them over all the bottom line. So in other words, first the bottom is 1, so we're going to take the entire top line, all those blue numbers, and put them over 1. So we've got 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, and 12 over 1. Then we put them all over 2. 1 over 2, 2 over 2, 3 over 2, 4 over 2, 6 over 2, and 12 over 2. Then we put them all over 3. 1 over 3, 2 over 3, 3 over 3, 4 over 3, 6 over 3, 12 over 3. Then we put them all over 6. 1 over 6, 2 over 6, 3 over 6, 4 over 6, 6 over 6, and 12 over 6. When we reduce these, we're going to get a lot of repeats and a much simpler list to work with. So 1 over 1 reduces to 1, 2 over 1 reduces to 2, 3 over 1 to 3, 4 over 1 to 4, 6 over 1 to 6, and 12 over 1 to 12. The rest are all going to be our fractions. 1/2. 2 over 2 reduces to 1. That's already in our list, so we're not going to repeat it. 3 over 2. 4 over 2 reduces to 2, which we already have, so we're not going to repeat it. 6 over 2 reduces to 3. We have that. 12 over 2 reduces to 6. We have that. 1/3, that's a new one. 2/3, that's a new one. 3/3, that reduces to 1. We have that. 4/3. 6/3 reduces to 2. We have that. 12/3 reduces to 4. We have that. Then there's 1/6. 2/6, which reduces to 1/3. We have that. 3/6 reduces to 1/2. We have that. 4/6 reduces to 2/3. We have that. 6/6 reduces to 1, and 12/6 reduces to 2. So we'll cross that one out also. So we've got this new list, and it looks like a long list, but it is a list of the only possible rational roots to our original problem. 1, 2, 3, 4, 6, 12, 1/2, 3/2, 1/3, 2/3, 4/3, and 1/6. And because this is a third power, 3 of those probably work. We just don't know which 3. This is why we learned synthetic division yesterday. We're basically going to use synthetic division to factor out each of these roots as fast as we can to hopefully find somebody who works. So we'll just start working down our list, starting with 1, and we've got coefficients of 6, 13, negative 19, and negative 12. Well, the 6 comes down. 6 times 1 is 6. 6 and 13 is 19. Times 1 is 19. 0, 0, negative 12. We're looking for a remainder of 0 if it's a real root. 12 did not work, so 1 is out. So we try another number. We got to try both the positives and the negatives of each of these rational roots. So we're going to try negative 1. So let's do 6, 13, negative 19, negative 12. 6 times 1 is negative 6. 7 times negative 1 is negative 7. And that's going to give us negative 26 and 10, 26. And you can tell this is not going to give us 0. So 1's out. Going to take up a lot of space, but we've got our list of roots here. Let's try 2. Coefficients were 6, 13, negative 19, negative 12. 6 times 2 is 12, plus 13 is 25, times 2 is 50, minus 19 is 31, times 2 is 62. That's definitely not going to give us 0 at the end. So that one's out. 2 doesn't work. We'll try negative 2. 6, 13, negative 19, negative 12. Bring down the 6. Times 2 is negative 12. 1 times negative 2 is negative 2, which gives us negative 21. Times negative 2 is 42. That's not going to give us 0 either. So 2 and negative 2 both don't work. They are out. Let's try 3. 6, 13, negative 19, negative 12. 6 times 3 is 18. 18 and 13 is 31. Times 3 is 93. 93 minus 19. You can tell this number is just way too big. Once you get a feeling that the number is getting way too big, we can cross it out. as well. So now we try negative 3 with 6, 13, negative 19, and negative 12. 6 comes down. 6 times negative 3 is negative 18. Gives us negative 5 times 3 is 15. 15 and negative 19 is negative 4. Times 3 is 12. And look at that. We got our 0 that we were looking for. We have a winner. X equals negative 3 is a factor, or is a solution. To get the factor, we have to add 3 to both sides to make it equal to 0, right? X minus 3 equals 0. So x minus 3 is a factor of our original problem. What's left becomes the remaining factor. And if you remember, we started with x cubed, so we will do x squared, x, and minus 4. So we have 6x squared minus 5x minus 4. And now that it's a quadratic, we can factor it using that guess and check method that we are so familiar with now. 6 is probably 2x times 3x. 4 might be 2 and 2, but that would be putting a 2 with a 2x, and there's no GCFs allowed. So it must be 4 and 1, and 4 can't be with the 2, because that would have a GCF as well. So I'm looking at negative 4, positive 1. Will give us that negative 5 in the middle. And we have now factored our original polynomial. X plus 3, 2x plus 1, 3x minus 4. Notice the other roots, if we had solved them. The roots would be 3, negative 1/2, and 4/3. And those are all on our list. 3, 1/2, and 4/3. So as we had gotten to those would have worked and the others would not have. So this process, it's going to be the exact same process for every single problem. It's really a educated guess and check process almost. Don't spend time trying to find the correct answer the first time. Start using synthetic division and just start pulling out your possibilities. First, we started with our factors of the last term, factors of 12. Then we considered factors of the first term, factors of 6. And that allowed us to make all of our possible roots by making fractions out of those. P over Q, P over Q, P over all the Q's, P over all the Q's. Reducing those just gave us a nicer list that we could work with. And then came the synthetic division until we stumbled upon one that worked. Every problem is the same. These just take some brute force to work out. Some of them get big and ugly. Some of them aren't so bad. Let's try and factor x to the 4th minus x cubed minus 3x squared plus 5x minus 2. 2 is our p. That's nice. It only has factors of 1 and 2. Our q, that's the front number of 1, and that's really nice. It's only got a factor of 1. So for our roots, PQR, P's, Q's, and roots, it's going to be the P's over all the Q's, or 1 over 1 and 2 over 1. Which will reduce to 1 and 2. Only possibilities here, 1 and 2. Maybe negative 1 and negative 2. Some people like to label those plus and minus, so they don't forget positive 1, negative 1. Positive 2, negative 2. So let's start with the positive 1. We got 1x to the 4th, negative 1x cubed, negative 3x squared, 5x, and negative 2. Bring down the 1. 1 times 1 is 1. Brings down a 0. 1 times 0 is 0. Negative 3 times 1 is negative 3. Plus 5 is 2. Times 1 is 2. And look at that. It worked out to a 0 our very first time. This means x equals 1 is one of our solutions. Subtract 1 from both sides, and we have x minus 1 equals 0. x minus 1 is a factor. So essentially we have x minus 1 times the stuff that's left, x cubed plus 0x squared minus 3x plus 2. But we still have a cube. So we still need to keep working on it. We're going to pull out another root. We want to get down to a quadratic with just x squared so that we can use just our normal factoring methods. So we've got the x minus 1. We need another one. We can even just work right underneath if we wanted to. But when we do, use the smaller, fewer numbers. Don't go back to the original looking for more factors, because that's more work. We've now reduced it down to 1, 0, negative 3, 2. So let's go from there. Another thing to note is we need to still test 1. There might be more than a single 1 as an option. So we're going to test 1 again. So bring down the 1. 1 times 1 is 1. Plus 0 is 1. Times 1 is 1. Minus 3 is negative 2. Times 1 is negative 2. Comes out to a 0. Notice the 1 worked again. That means x equals 1 is another solution. So if we subtract 1, x minus 1 is another factor. So we have the original x minus 1, our new x minus 1, and what's left is 1x squared plus 1x minus 2, pulling that from the bottom row. And now that that's just x squared, we can factor that using the methods we're more familiar with. X squared is x times x, and 1 times 2. To get the negative 2, we need a positive 2 and a negative 1, so that's going to be x minus 1 cubed times x plus 2. And the advantage of the cube is it's going to help us as we try and graph this polynomial. We can see that the zeros are at 1 and negative 2, but the 1 was a cubic. So 1 and negative 2, but the 1 was a cubic. The original problem was a positive x to the 4th, so we know it comes down from the top right. As it comes towards the 1, because it's a cubic, it's going to level off, not just go through it and go up. And we're able to graph our polynomial. This is x to the 4th minus x cubed minus 3x squared plus 5x minus 2. So the big thing we learned in this example is once we have found a 0, if we're going to still look, use the abbreviated, simpler form. Use those numbers that we just found, not the original numbers. It's going to be easier. Another thing we learned is make sure just because 1 came out, we still have to test 1 again. We have to test every root until it fails. We saw a lot of failing in the first example. Once they failed, we cross them out. But don't cross them out until they fail. If they succeed, they might be successful again. Let's do one last example. 12x cubed plus 8x squared minus 3x minus 2. We're going to factor, and if we have time, we'll graph it as well. P's come from the end. 2 is nice. It's only divisible by 1 and 2. Q's come from the beginning. 12 has a few factors. It's divisible by 1, 2, 3, 4, 6, and 12. And so for our possible roots, we put the 1 over all the Q's, and the 2 over all the Q's. So first we put them over 1, 1 over 1, 2 over 1. Then put them over 2, 1 over 2, 2 over 2. Put them over 3, 1 over 3, 2 over 3. Put them over 4, 1 over 4, 2 over 4. Put them over 6, 1 over 6, 2 over 6. Put them over 12. 1 over 12, 2 over 12. Now we can go through and reduce, and as we do, we'll get rid of our repeats. 1, 2, 1/2, 2 over 2 reduces to 1. We've already got that. 1/3, 2/3, 1/4. 2/4 reduces to 1/2. We have that already. 1/6. 2/6 reduces to 1/3. We have that already. 1/12. And 2/12 reduces to 1/6. We have that already. So now to find our correct roots, just have to start working through. Start with our 1. Coefficients are 12, 8, -3, and -2. Bring down the 12. Times 1 is 12, plus 8 is 20, times 1 is 20, minus 3 is -17, and you can see this is not going to give us a 0. So let's try -1 with 12, 8, -3, -2. Bring down the 12. Times -1 is -12, plus 8 is -4, times -1 is +4, plus -3 is 1, times -1 is -1. Not quite. Not going to work for us. So the 1's out. We tried the plus and minus. Don't forget, very important, you got to try plus and minus all the way through, positive and negative on each one of these. Checking both. So 1 didn't work. We're going to try 2 with 12, 8, -3, and -2. 12 times 2 is 24, plus 8 is 32, times 2 is 64. I can see already these numbers are getting huge. Probably not going to work. Let's try -2. With 12, 8, -3, and -2. Bring down the 12. Times -2 is -24. Plus 8 is going to be -16. Times -2 is 32. Again, it's getting huge. It's not going to go away. So the 2's are out. Now we get to the fractions. And really there's no best fraction to try. You might think, hey, I feel like we do better with the negative. So maybe I want to try -1/2 first. Let's see, with 12, 8, -3, and -2. 12 times 1/2 is -6, plus 8 is 2. -1/2 is -1, which gives us -4. -1/2 gives us 2. -2 and 2 gives us 0. And look at that, we've got our 0. So since we have a solution, we say x equals that solution. X equals -1/2. So if we add the 1/2 to both sides, we get x plus 1/2 equals 0. And x plus 1/2 is a factor then. What's left becomes the 12x squared plus 2x minus 4. Checking for a GCF first, we can pull a 2 out of there. 2 times x plus 1/2 times 6x squared plus 1x minus 2. And 6x squared is probably 2x times 3x. The 2 is probably 2 times 1, and we can't put the 2 with the 2. No GCFs allowed. So if we do a positive 2 and a -1, that's going to give us that in what we want in the middle. Another thing I notice is distributing the 2 through the parentheses is really nice because it's going to clear that fraction. So that's what I'm going to do. I'm going to do 2x plus half 2 is 1. And now it is completely factored. 2x plus 1, 2x minus 1, 3x plus 2. We can even graph this because we know our solutions are -1/2, +1/2, and -2/3. And so if we were to graph it, there's 1, negative 1/2, positive 1/2, and negative 2/3 is going to be right there. Going back to the beginning, it was a cubic, so it's going to come in from the bottom. Went too far. It's going to come in from the bottom, wiggle, and go out the top. The y-intercept, when you figure it out, turns out to be negative 2. So that's the rational root theorem. It's a big plug-and-chug system, but it works every time. It'll find you your factors. What we're going to do is we're going to identify our p and our q and all of those factors, use that to come up with all of our possible roots, and reduce them. And then lots of synthetic division to see which ones work and which ones don't. Take a look at the homework and practice these, and come to class with questions.